demonstrations project, we are going to show the distribution property of the triple vector product. We are going to derive this property using three different methods. First method is just direct calculation of one component of the triple vector product and see how this component distributes into different factors. The other method is a geometric method in which we use properties of the vectors and using a little bit of geometry properties to show how to demonstrate the triple vector distribution property. This is interesting to gain insight on vector algebra. And finally, we make another type of demonstration in which we use the Kronecker delta function as well as Levi-Civita symbol to make in an objective way to make this demonstration of this distribution property of the triple vector product. You can see in the videos that we are going to have time points where you can jump directly to the type of demonstration that you are interested in. So here is the video. What we want to show is that we have this property A cross B cross C, the distribution type of property equals to AC B minus A dot B C. This is what we call the distribution property of the triple vector product. What we are going to do is to calculate the W components of the left hand side. And if we show the property for one component by simple cyclic permutation, we can show the property for the other components. So let's say that we have the double components, which is AU. Let's put like this, right? A cross B cross C W components. So it involves the U component of U, the V component of the other factor, B cross C V components, minus V component of U times B C W U, right? Then we expand the B cross C, is going to give us EU. The V component is the W and U, BW, CU minus BU, CW. And the other one is AV. U components, that's VW, BV, CW minus BW, CV, okay? Well, we have several terms here. We can almost identify a dot product. For instance, a B with C, we have A with C, which is this factor here, is almost here, right? A with C, we have AU, CU, right? We have AV, CV. Both terms have a BW in common, so let's make a BW as a factor. So we're going to have AU, CU, which is this factor here. And the other one is AVCV, so that's a plus, right? Minus and minus. I'm sorry, plus, that's not B, yeah. AVCV. So we got this term here, right? And we got this term here. There's the other term that's left is CW in here is a common factor, right? So what we have minus, minus CW, right? So we have this CW here, we have AU, BU plus, right? We have another CW here, is a common factor, minus AV, BV. So we're going to have minus AV, I'm sorry, let me see if I make something. Oh, sorry, this is a minus here, right? This is a minus sign. Here is also a minus sign. So we have to put minus as a factor. So we're going to have a plus here, AV, BV, right? So what is missing here to complete the dot product of A and C, as well as here, what is missing here to complete the dot product of A and B is the term plus AW, BW. So I can sum AW, BW and subtract this times this, minus AW, I'm sorry, the missing terms is AW, CW. I can add this term and subtract the remaining, which is BW times AW times CW. Same thing here, right? We have to add AW, BW, and subtract the same quantity inside, which is AW, BW times the external factor CW. When I do that, this minus with this minus is plus, which is cancels this minus here. So when I do this, I have cancelled this term with this one here. Okay. Notice that in practice, this term here is going to be minus with minus equals plus, and this term here is going to be minus, which I included, with plus, which is minus. Minus AW, BW, CW. Here is going to be plus AW, BW, CW. So we cancel those terms. And here we have a perfect dot product, okay? Here we have BW, then I add this term here, we have a dot product, right? AU, CU plus AV, CV plus AW, CW minus CW, we have a perfect dot product again here, AU, BU plus AV, BV plus this term here, AW, BW. So what do we have here? We have BW, we have dot product between A and C minus CW, dot product between A and B, right? So what we've shown is that A cross B cross C components, W component is related to the W component, BW, right? AC minus CW AB. Now, if you use cyclical permutation, you can show that this for U is valid also, as well as for V. So that completes the demonstration, right? A cross B cross C equals to ACB minus ABC, AB dot C. Okay, so that's our final expression as we wanted to demonstrate the distribution property of the triple vector product. So we want to demonstrate the distribution property of the triple vector product, which is this one. First of all, if B and C are parallel, let's say that C is a multiple of B, the result is going to be 0. The left-hand side is 0. And the right-hand side is going to be something like A dot KB times B minus A dot B times KB, right? Which is equals to KB times B minus KB times B, which is 0. So we have 0 equals 0, and the identity is verified for the case of C and B collinear. Let's make now C and B non-collinear, right? So they have an angle between them, non-parallel, let's say. Instead of working with vectors, let's work with versors. Let's see what is A versor times B cross product with C versor. Notice that if you have B and C, so the cross product is orthogonal to both, okay? And the cross product of this B cross C versor, right, is orthogonal to B cross C. So so if we have A cross B cross C, this versor is going to be in the plane formed by B and C. So that's what we have. So what we have, A cross B cross C, right, is a versor that's orthogonal to B cross C, which is going to be in the plane parallel to B and C, on the plane B that contains B and C. So it means that A cross B cross C, being in the plane formed by B and C, can be made as a linear combination of those two versors. Let's say P times B minus Q times C. So these are two scalar factors that we can have, okay? Now, if we make a dot product of both terms with A, we're going to have a 0 on the left-hand side because it's going to be A cross a vector that's orthogonal to A. So A dot A cross B cross C equals 0. So this is going to be P A dot B plus Q A dot C, right? So this equals 0. It means that I can express one of the factors as a function of the other one and the other dot products. For instance, Q can be written as a factor minus P A dot B divided by A dot C. So it means that A cross B cross C is equals to PB, right? This factor here, plus Q, which now is given by this, minus P A dot B divided by A dot C times C. Let's call this a factor. I can put I can put this like this, P divided by AC. Then we are going to have ACB, right? Minus ABC, right? So that's what we have. That's what we have, right? So we can call this a K factor. So A cross B cross C equals to a factor K. Then we're going to have ACB, is almost there, right? ACB minus ABC. I mean, that's for the versus only, right? Not for the vectors yet. But for the versus, it's starting to look like the identity that we are searching for. Well, this constant can be determined, is a single constant, right? Can be determined whatever are the combinations that I use for those verses, okay? In particular, I can choose, for instance, A equals B, right? A equals B, and A orthogonal to C. So what we're going to have is A cross C, in which those verses are orthogonal. So that's going to give me K. So observe that A and C are orthogonal. So this term is 0. So it's going to be minus K. AB, A and B are equals, right? So A dot A equals 1. So minus K times C, right? That's what we have. So let's take a look on what is this in here. Let's draw it, right? So the assumption is that A equals B, and both are orthogonal to C. A and B, right? So we have the same verse. So that's what we have. Let's say we have an A here. Then we have C is orthogonal to A. Let's do it like this, right? A cross C is orthogonal to both, like this. And A cross C is a versor that goes this way, magnitude equals 1, which equals to A cross C equals to minus C. So this is equals to minus C, which is equals to minus KC. So it means that K equals to 1. So that's what we have, right? So that's what we want to determine for a specific choice. So we have this identity here. Let's pick it up and put in the other view graph. Let's put here. So that's what we have. K equals 1, so in other words, A cross B cross C equals to AC B minus A B C. If I wanted to generalize this for vectors, I just multiply, let's say that A equals to A times A, B equals to B times B, and C, and C equals to C times C, right? So what I'm going to do is to multiply both members to ABC. So what we have? Well, we have what we expected. AA cross BB cross CC equals to, then I can join the similar things here, AB. So it's going to be AA dot CC times BB minus AA dot BB times CC. So that's ACB minus ABC. So this demonstrates our distribution property of the triple vector products using this method. It's a semi-geometric method, let's say. So this concludes our demonstration of the triple vector product distribution property. Well, the other way to demonstrate the triple vector product, not like this, I think it's like this. The triple vector product identity or distribution property is to use, those repeated indices that indicate sum, which is Einstein's method, together with Kronecker delta function and the Levi-Civita symbol. We assume that the viewer is used to those symbols. So we can write in this case, this in compact notation is going to be AI cross B cross C is going to be BJ CK epsilon, which is the Levi-Civita symbol of JK, let's say AL. That's the direct notation for the vector product. Then we have another cross product here. So we're going to have AI BJ CK. So that's going to be epsilon of I L M, right? The cross product of AI with AL is going to be epsilon I L M A M. So we have times epsilon J K L A M. Okay, so that's what we have. Now, it's important to notice that those two Levi-Civita symbols have a same factor L in common. It means that this product can only be non-zero if the other indices are kind of equal. Let's see in what conditions, right? So we want to look at this product here. Epsilon ILM times epsilon JKL. Let's make a permutation on this index here, a cyclic permutation without changing the sign. So this is going to be epsilon like this, right? That's a permutation like that. So L is going to be the final index. It's going to be epsilon of M IL times epsilon JKL. So this factor has only two possibilities. It's going to be equals to 1 if M equals J and I equals K. And it's going to be minus 1 if M equals K and I equals J. Okay? So that's simple to see this. So this is equals to, in fact, a product of canonical delta functions. Delta Mj delta Ik minus delta Mk delta Ij. So we have then the A cross B cross C equals to this term here, right? AI, Bj, Ck, epsilon I, Lm, epsilon J, Kl. Let's substitute by the delta function effect. It's going to be delta Mj delta Ik minus, one of them is 0, the other is non-zero if the condition is violated. So delta Mk delta Ij times Am, right? The versor is Am. Now, under this condition, I can make J equals to M here. I equals to K. So it's going to be, the first term is going to be AK. J equals to M, BM, CK, right? AM. Minus the other case, K equals M and I equals J. So it's going to be AI, BI, I equals J, right? Then it's going to be C, K equals M, CM, AM. So we can identify here AK, CK times BM, AM minus AI, BI times CM, AM. So repeated indices mean sum. So this is A dot C, this is B, minus A dot B times C, which is this one. So that demonstrates the distribution property of the triple vector product A, C, B minus A, B, C, as we wanted to demonstrate.